Hello, welcome back to Math 332 Linear Algebra, and this is a video on change of basis. So in this sections, we are going to study how do you change the coordinates with respect to different bases through a matrix which is known as the transition matrix. So a quick review. So you go back to your notes all the ways to the concept of coordinates. You will remember that in order to define coordinates, we will have to have a basis. So you first encounter the concept of coordinates in section 4.4. And so if you remember, once we have a basis for a vector space V, the coordinates of this vector V is given by all these coefficients. So because bases span this space, so if you take a vector V that is from this space, you can definitely find all these numbers so that V is equals to C1 over V1, C2 of V2, and so on and so forth. So in these particular expressions. And we prove that these numbers here, there's only one way you can write all these numbers. So the expressions of this vectors V in this form is unique. And therefore, by selecting all these numbers and put them into a column vectors, that gives the coordinates of these vectors. So as I said, coordinates of a vectors is always a column vectors that looks like this. The vector space could be vectors of polynomial, could be vectors of matrices. It doesn't really matter. The coordinates is always Rn. Doesn't really matter what kind of elements that is in that vector space. So vector space could be some strange thing like polynomial and stuff, but the coordinates is always a column vectors of numbers like this. Okay, like this. Now we also mentions that before that because the definitions, the way we define definitions depends strongly on the kind of basis that we choose. And for a vector space V, we know we might have multiple different bases. We can actually have many, in fact, infinitely many different bases for a vector space. So because of that, we have to be slightly more careful by indicating coordinates. And that's the notations for how you write coordinates once you know what kind of basis are you looking at. So again, last time, long time ago in high school and universities, when you write coordinates, you never have to refer to what kind of basis are we looking at, because we are always refers to the standard basis. And if you are in R3, your standard basis is always a IJK. So there's no need to indicate, especially like what kind of basis are you looking at, because we are always just using one basis. But from now on, we can actually use different bases. And from your homework and also in class, you see that why sometimes we have to use different bases. Because different bases sometimes is actually the other type of basis that's different from the standard basis is sometimes more useful. It's more convenient to do that. All right, so we quickly review the concept of coordinates, and always remember coordinates will depends on what kind of basis are you looking at. All right, so if you're looking at this basis S, then the notations for the coordinate of this vector with respect to basis S is given by this column vectors, and we have seen an example like this before. So if you are in R2, you have a vectors 4, 5. And if you are referring to the standard basis, the coordinate is obviously 4, 5, because you need 4 of this, okay, and 5 of this to make 4, 5. That's pretty straightforward. And you're also seeing that we can have a different basis in R2. So now, same vectors, what is its coordinate respects to S2, this different basis? Well, it's not so straightforward anymore. You can't just see it immediately that it's 4 of this and 5 of this. It doesn't work that way anymore. But by the definitions, always remember the definitions, what you need to find for this coordinates is this constant. So you need to find these numbers K1 and K2. How many K1 of this vectors you need it, and how many K2 of this vector you need it, so that the sum will give you 4, 5. And solving this system of equations, it will give you 2 equations, 2 unknown, and you solve them, you realize that I actually need 3 of these vectors and 2 of these vectors to make 4, 5. So by the definitions, 3 and 2 will be the coordinates of these vectors in R2. So that's the notations, and you can see it's straightforward. We try to find this constants K1 and K2, these numbers, real numbers, and put it as column form, and that will be the coordinates of a specific vectors. And you can see again, this apply to many different type of vector spaces. So let's say P2, same definitions. What's the coordinates if you refer to that standard basis? So this is 1, 2, and -1. So this polynomial has a coordinates 1, 2, -1 if you refer to this standard basis. Slightly harder is that, hey, if you use this basis, so B2 changes to this basis, same polynomial, what are the coordinates? So you have to solve this, right? You take K1 of this, K2 of this, and K3 of this, and you want to find these numbers. These numbers, by definition, will be the coordinates of this polynomial, same polynomial as the one that we have before, but with different bases. So now with basis B2. So if you solve it, here, okay, I didn't write all the things out, but if you write these things out, comparing coefficient, and you will see that you will get 3 equations and 3 unknowns, and you solve for it, you will get K1 is actually 2, K2 is 0, K3 is -1. So this polynomial with respect to this basis B2 is 2, 0, -1. And as I said many times, even though the vector space is polynomial, spaces consist of polynomial of degree at most 2, the coordinates is not a polynomial. The coordinates is an element in R3. Okay, so that's that. So now this is just review on the concept of coordinates, and now let's get to the questions of today, which is this one right here. So now you have a vector space is finite dimensional, which means that if you find a basis for that vector space and you count the number of vectors in the basis, you will see that it consists of finite number of vectors. So the basis consists of finite number of vectors, and that finite number of vectors, number of vectors in that vector space, the number of vectors in that basis is defined as the dimensions. So this is again review. So when you say finite dimensional vector space, means that the vector space which has a basis which consists of finite number of vectors. All right, so we have basis, right? We have basis. So let's say vector space V has 2 different bases, and we label them basis B and basis B prime. Okay, as the example that we have before, pick a vector V, fixed vectors from that vector space big V, and we want to write the coordinates. So if you want to write the coordinates, if you write the coordinate with respect to this basis B, you will get this. This is going to be element in Rn if this finite dimensional vector space actually has dimension n. And you find another coordinate, this time with respect to the different basis B prime. So this is again another element in Rn, again assuming that the dimension of that vector space V is n. So the question now is, we have these 2 different bases B and B prime. We have these 2 different coordinates with respect to this basis B prime and B. How are they related? So do we have a relationship between, okay, let's get rid of this. So do we have a relationship between this vectors and, this vectors, these Rn vectors, this coordinate and this coordinate? Okay, so let's look at how we do it. And in fact, let me just tell you the answers without proving it first, just let you know what's going on. So again, let's look at this example right here. Say you have a vector space V. We don't even care what kind of vector space is that. But I mentioned that the dimension of the vector space V is 2, which means that if you have a basis, the number of vectors in the basis is 2. Okay, so let's start with this basis B prime. So B. This basis B consists of 2 vectors, U1 and U2. B prime, another basis, consists of 2 different vectors, U1 prime, U2 prime. Now, the relationships of the vectors V, the coordinates of the vector V, respects to B prime, and the coordinates of the vectors V respects to B is connected like this. It's connected like this, okay? This is an Rn vectors, so in this case R2. This is a column vectors R2. They are related by multiplying this vectors V, coordinates V with respect to basis B with this 2x2 matrix. And this 2x2 matrix is obtained, okay, is obtained, that's the key. This 2x2 matrix is obtained like this. So you take this U1, so let me erase all this. So you take this vectors, okay, and write its coordinates with respect to this basis. So put it right here. Put it right here. Take U1 and write the coordinates of U1 with respect to this basis. We know how to do that. And put it as a first column right here. And then you take U2, and again takes the compute the coordinates of u2 with respect to this basis, and you put it right here at the second column. And that's the notation for it. The coordinates of u1 respects to b prime, put it as the first column, and the coordinates of u2 with respects to b prime, and put it as the second column. This is what that notation means. Okay, this notation means that, and the relationship is given by this. And this matrix right here is denoted as P, B to B prime. Now, this is strange right now, but all this notation makes sense. So let me explain this a little bit. All right, so let me explain this a little bit. Now, so this is a vectors. This is a column vectors. This is actually the coordinates of vectors V with respects to basis B. Now, if you multiply it with this matrix, which is written like this. The reason why it's written like this is because we can't think of it like a function. So this is kind of like an input. So the input is a coordinate with basis B. So it will pass this basis B to basis B prime. What this matrix does is kind of like passing the coordinates with respect to basis B to B prime, and then you will get the coordinate of the same vector V, but this time is with respects to the basis B prime. So that is why this relationship here is written as like this, with this matrix, transition matrix is known as transitions matrix, with notation that looks like this. So it's kind of like you view this as a functions, put this as an input, put it inside here. You see this is coordinate respects to basis B, and you pass it to B prime, and you get the coordinates for the same vector V, but this time with different bases, with basis B prime. So you see that it's passing from B to B prime. That is why this notation is given like this. Okay, so I haven't explained what happened here yet. I didn't explain like why this is true. I'm just telling you how to compute them. And now, without looking at the proof, let's look at a computational example first. These are the proof, but let's look at a computational example, which is, okay, let's skip this one first. Let's look at a computational example right here. So right here, let's look at this one first. Okay, so our V, okay, is a polynomial. It's a vector space, consists of all the polynomial of degree at most 2. So we have two different bases. So we have basis B and basis C. We actually showed that before. These are the two different bases for the vector space P2. Okay, so now let's say I want to find the transition matrix. So let's say I want to find the transition matrix P from C to B. Okay, from C to B. All right, so which means that, okay, I will have to take vectors that is in C. So I have to take vectors that's in C. Do not do that though. Do not do 1 plus x, because we are not taking the elements of this basis. We are not looking at the element. We are looking at the coordinates of this element. The coordinates of this element with respects to B, and put it as the first column. Okay, so okay, and then you do the same thing. You take the second element, x plus x squared, right? Not the polynomial, but the coordinates, okay, with respects to this basis B, and put it right here as the second column. And do the same thing for 1 plus x squared, not this polynomial, but the coordinate with respects to basis B, and you put this right here, and that will be your transition matrix from C to B. Okay, so how do we compute that? Easy. Why is it easy? Because B is the standard basis. So it's a standard basis. So if you take 1 plus x and you want to find the coordinates of 1 plus x with respects to this basis B, so 1 plus x is obviously 1 of the 1, 1 of the 1, 1 of the x, 1 of the x, and then 0 of the x squared, 0 of the x squared. So the coordinate of 1 plus x is 1, 1, 0. It's always an element's coordinates. Let me say that again. The coordinates of vectors is always an element in Rn. So this vectors is a polynomial, but the coordinate is not a polynomial. It is 1, 1, 0. So you put it inside here. This is going to be 1, 1, 0. 1, 1, 0. Okay, as you can see, that's the 1, 1, 0 right here. Okay, now same thing. I need to compute x plus x squared. What is the coordinates? Well, the coordinate respects to b. B is the standard basis. So you just read off the coefficients, 0, 1, 1. Straightforward. That's the reason why you have 0, 1, 1. And then what is, so when you're done with this, what is 1 plus x squared? Not the vectors, but the coordinates, right? That's the third column. So because you are referring to the standard basis, b, so you just read off the coefficients, basically. So you have 1, 0, 1, and that's go right here. So that will be your 1, 0, 1. So this will be the transition matrix from C to B. So try not to memorize it using... so the problem with this kind of question is that, you know, it's very easy to get yourself confused because notation wise is kind of messy. You have like B to B prime, then you have to like B prime, blah, blah, blah. It's just very difficult to remember. The way I remember it is if you want to have a transition matrix from C to B, right? C to B, this is where we start. So this is like your starting basis. So you put the elements, all the elements, okay, of your starting basis here, but you write as the coordinates of the other one, of this basis, this basis. So this is like starting, this is like ending. So you start from the starting, right? That's 1 plus x, x plus x squared, and 1 plus x squared. And you write the coordinates with the respects to the ending basis. So you write down, and that will be the transition matrix, because we will not always write basis BC. Sometimes you see like the problem is like basis B prime. There are many different notations. So don't memorize the notations. Don't memorize the letters, the notation, but memorize the positions of the all these bases. So start from basis C, end with basis B, take elements from basis C, write the coordinates with respects to B. Take the element, okay, take the elements from basis C, take the element from basis C, and write the coordinate respects to B. Take the element from basis C, the starting basis, and write the coordinates with respects to B, right here. Take the element from basis C and write the elements with respects to the basis B. Writes the elements, the coordinate of the element respects to basis B. So sometimes you see books saying that the starting basis, ending basis. This is how you remember. Starting, ending, not the letters. Okay, if you try to memorize the letters, you get yourself into a big problem. Okay, so let's go back and look at another problem. Okay, let's go back and look at another problem. The problem is right here. Okay, so let's look at another application problem. We haven't talked about why this method works yet, but we're just showing you how to compute them. Okay, so now let's look at this example one more time. So now we are in R2. So in R2, we have two different bases. So this is basis B and this is basis C. So basis B consists of vector U1 and U2. This is U1, U2. Basis C consists of vector V1 and V2. This is V1 and V2. Okay, so the question now is, find, okay, so find, let me put this thing down a little bit. Find the transition matrix B to C, okay? Find the transition matrix B to C. So this matrix, okay, again, take the starting vectors. So take U1, but not putting U1, but you put U1, the coordinate of U1, with respect to C, and put it here. Okay, why? Because this is the starting, this is the ending. So you take starting vectors, okay, but write the coordinates, not the starting vectors, but write the coordinate of the starting vectors with respect to basis C. Okay, all right, so take starting vectors U2 and write the coordinates with respect to basis C. So right here, that will give you the transition matrix P from B to C. So let's compute that. Okay, so you take U1, this is your U1. So you take U1 and write the coordinate with respect to C. So the question now is U1, okay? So this is your U1. You want to find the coordinate with respect to C. So the basis C consists of vectors V1 and V2. So you have to find this coefficient. So let me remind you one more time. This basis B has vectors U1, U2. The basis C has vectors V1, V2. So if you want to write U1 as the coordinate, you want to find the coordinates of U1 with respect to basis C. So U1, okay, coordinate basis C, meaning that I need to know what are these two numbers. Why? Because that is exactly the definitions of coordinate with respect to basis C. If you are looking at coordinate with respect to basis C, write the vectors here, which is in C, and try to find the coefficients. After you find the coefficient, this coefficient go here and here. All right, so this means that solving this system. So solving this system, will give you look at the RREF matrix right here. You will see it. You give you will see that you give this one. So solving this system, okay, you have this. That is your K1 and K2. This K1 is -3, K2 is 2. All right. So the coordinates of U1 with respect to basis C is -3, 2. All right, -3, 2, which means that right here, this is -3, 2. Okay, now U2, coordinate U2 respects to basis C. So U2 respect to basis C. These are vectors in the basis C. Okay, so you need to find these two coefficients, which means solve for this, which means do this. Okay, and you'll find that in this case, this is 3, this is -1, and you can double check and you'll see that it is true. So the vector U2, not the vector U2 though, the coordinates of vector U2 respects to basis C, okay, is given by 3, -1. So 3 -1s goes here. See the coordinate, okay? 3 -1s goes here. So this is the transition matrix. So this is the transition matrix from B to C. So the transition matrix from B to C, so transition matrix from B to C is given by this. Okay, now that is everything from definitions. Everything is from definitions, nothing fancy. But if you go through this computation right here, so you know that to find all these coordinates, all these coordinates, we need to solve for the K1 and K2. We need to solve for the K3 and K4. And you actually see that when you solve K1, K2, K3, K4, you're doing this computation right here. And you can see the coefficient matrix is always the same. When you try to solve, for this systems, when you try to solve for system 1 here, okay, the coefficient matrix is 1, 0, 1, 1. Okay, when you try to solve for the system 2 here, you will see the coefficient matrix is also 1, 0, 1, 1. So the coefficient matrix for these two systems is always the same. The only thing that's different is these two vectors. This vector here is different. This vector here is different. So instead of using your calculator, so this is short form. This is a easier way, but you don't have to do it this way. You just can just follow the definitions. Who cares? Okay, but if you want to be slightly more efficient, you realize that, well, the system always share the same coefficient matrix. It's only this thing here is different, which you can see is here, and this thing here is different, which you can see is here. So instead of solving it twice, you can also do it in one shot using your calculator, which is put the coefficient matrix here, and then put this thing right here, and put this thing right here, okay, and solve for it. And we solve for it, okay, using the same coefficients matrix. This is your solution for K1 and K2. And this so happened to be this coordinate, okay? Because, why is this? Because your K1, K2, right, is K1 of V1 and K2 of V2. So this is the coordinates of U1 with respect to C. So happened, okay? So when you solve for the second system, you're solving right here, and you get this. So this is your K3, K4. This is your K3, and this is your K4. And it's because we define K3, K4 like this, this so happens to be the coordinates of U2 respects to C. So some books, which I don't really like, will say that in order to compute the change of basis formulas, you just have to put all these things together and solve it like that, and whatever this thing is, that will be the coordinate. There's a reason behind it. The reason behind it's nothing fancy. It's just solving system 1 and system 2. And this is just, instead of doing it system 1, solving system 1 and system 2, instead of doing it twice, you put them together and do it like one time using your calculator. It's nothing fancy that this turns out to be what we want. This is nothing fancy that this turns out to be the exact transition matrix that we need. Okay, but the key reason is not because of that. The key reason is this is just a shorthand notation. The key reason is because you solve this, because we need to figure out what's the coordinates of U1 respect to C, coordinates of U2 respect to C. So you can always just follow the definition and do it. And this is like shorthand notations. You can reduce the number of computations by just putting all this coefficients matrix together, same coefficient matrix. The only thing that's different is this and this. So you put it here, and you row reduce and solve for K1, K2, K3, and K4. So this is how you get that. Okay, so now, for application purposes, once you have this transition matrix, then it's easy for us to find the relationship between any vectors x that is in vector space V. If you want to look at the relationship between the coordinates, you can do this computation. So for example, right here, suppose you know that x has x, the vector x, this is the vectors. If you try to find the coordinates of this vector x with respect to basis B, you have 1, 3. Okay, you have 1, 3. So this is given as 1, 3. Now, what is this basis, this vector x, this same vector x, but what is its coordinates if you are looking at the coordinates of these vectors with respect to basis C? Well, since you already find this is B to C, right? So this is 1, 3 is the coordinates with respect to B. So we will pass from B to C. So you multiply this thing out, you'll get 6, -1. And 6, -1 will be this vectors, same vector x, but the coordinates of that vector x with respect to the basis C. So this is 6, -1. So these are the same vectors. Nothing changed. But the coordinate change if you change the basis. So the same vector x with the coordinates with respect to basis B is 1, 3. With respect to basis C is 6, -1. And they are computed like that. Okay? So once you have the transition matrix, you use the transition matrix to do computations, to do conversion like that. Okay. So that's that. And I still don't want to talk about the proof yet. Let's just look at one more property, which is right here. Okay, and you can see now that with good notations, all this thing kind of makes sense. Now, so this is again one more example before we look at the proof. This will help us simplify a lot of computations if one of the bases is a standard basis. It will make things slightly easier. So now, imagine that you have vectors with a vector space with two different bases, B and B prime. Okay, so now you compute transition matrix. One of the transition matrix apparently will take the coordinates with respect to basis B and you will change it to B prime. And then another one will take B prime and change it to B. So imagine you are passing a vectors, the coordinates of a vector with basis B, you're passing a vectors, not the vector itself, but the coordinates. You're passing these coordinates to this matrix, then you will get, okay, passing means that this is with basis B, so it will pass to B prime. So this will give you a vectors, the coordinates of a vectors with basis B prime, okay, so this is B prime now, and then you will pass it back to B. So if you do this computation, your coordinates will be passing. So if you do these computations, your coordinate will be passing from B to B prime, and then from B prime back to B. See that? Okay, so starting from B to B prime, and then B prime back to B. So if you are multiplying these two transition matrix, you actually get a transition matrix that pass the coordinates from B to B, right? You start from B. Okay, let's do that one more time. You start from B, you end with B prime, and then you start with B prime, you end with B. So this is from B to B prime, and then B primes to B. So the product of these two matrices give you a transition matrix that pass a vectors with coordinate with coordinates with respect to basis B to the coordinate with respects to basis B. So nothing changed, right? So nothing changed. So the whatever coordinates you have here will be the same as whatever coordinate you have here because they pass through a new basis, but it passes back. So which means when you multiply these two transition matrix together, you get this transition matrix, which is the identity matrix because nothing changed. Whatever go into that multiplications will come out the same vectors. So nothing changed. So if you remember from the way we define inverses, if you have two matrices multiplied together and get identity matrix, then you know the relationship between these two matrices. The relationship between these two matrices is very simple. They are inverse of each other. This matrix is the inverse of this matrix. This matrix is the inverse of this matrix. So this gives us this relationship. The transition matrix from B to B prime is the same as the inverse of this. Again, the transitions of this matrix B prime to B is the inverse of this. Okay, so why is this important? This is important because, as you can see from this example, it is so easy to compute this matrix. It is so easy to compute this matrix. Why is it so? because we just need to write, this is a standard basis, so we just need to write 1 plus x, we just need to write 1 plus x, right? And write it as a coordinate with respect to this basis. That's a standard basis, so you just read 1, 1, 0. It's pretty easy. And the coordinate for this is 0, 1, 1, very easy. So this is a very easy transition matrix. That's my point. This is a very easy transition matrix. However, if I ask you to do the other one, which is B to C, this is not so obvious. So B to C, right? B to C. So you have to take this vectors, okay, which is 1, and you have to find the coordinate respects to this basis C. So you are asking, so in order to find this column, you will have to compute. In order to find this column, you will have to compute what is the constants K1, so that this is 1 plus x plus K2, this is x plus x squared, and then plus K3, this is 1 plus x squared. So you have to find K1 and K2 and K3 and put it here, K1, K2, K3. It could be easy, but it's certainly more complicated than this one, right? So this one is easier to compute because, well, if you want to write with respect to basis B, everything is straightforward. But you want to write at basis C, you always have to solve equation like this, which is more complicated. But with this relationship, I know once I have this, the other one is just the inverse of this. Oops. So as you can see, once I have this, okay, what is P? Okay, so I don't have to compute it like that anymore. Once I know this relationship, if you ask me, what is B to C? Well, if I can get this so easily, I can use my calculator and just like, oh, you want this one from B to C? You want it from B to C? This is actually the inverse of the one that is from C to B. So I already have C to B, which is this. So find the inverse, I will get the other one. So that is how you use this particular property right here to help you with the computations. Okay, so that is why in this case, let's erase all this and let us look at the question itself. Okay, so the question is you have this basis B and this basis C in this vector space. They ask you to find two of them, these two transition matrix. And actually, you know that this transition matrix is actually easier to find. So you found them, take the inverse, you will find this. So you found them, take the inverse, and you will see that this is the other transition matrix that is from B to C. That's slightly harder to find. Okay, and again, once you have this, if they give you, so for example right here, so if they give you, you have a polynomial px, and they want you to find the basis, the coordinate respects to this basis C, you can also see that this is, if you want to write this coordinates px, okay, we'll find the coordinates px respects to basis B. This is so easy because again, this is just 1, 2, negative 1. So this is so easy to compute because this is a standard basis. When you have standard basis, everything is straightforward. So again, this is a standard basis. So this is very easy to compute. So if they want you to find what is the coordinate of pxc, well, you will find this because this is easy to find and multiply with this transition matrix. And this transition matrix is computed this way, and you get that, and you get these answers. So these answers is that once you have 1, 2, negative 1s, once you have 1, 2, negative 1, put it inside here and multiply with this transition matrix, you will get this coordinates. So you got that. So once we get this relationship between these different bases, finding coordinates with respect to different bases is pretty easy now. You just keep multiplying with the actual transition matrix, and you will get the answers. So computation like that shouldn't be very difficult. Again, we can work on this entire concept with different vector spaces. So this example here show that how you should compute, how you will find all these transition matrix with different bases. Everything is the same. You should read these notes. Everything is the same. All the concept is the same. Just follow the concept. Computationally, they are all the same. So the only thing that's different is we are on a different vector space. So this is a vector space which consists of not all 2x2 matrices, but all the 2x2 matrices that looks like this. So this is not all possible 2x2 matrices because in this set, this entries here has to be 0. So these are the actual bases. So we know M 2x2 is dimension 4, but this vector space is actually smaller than this, and it's actually of dimensions 3 because these are the bases, and the number of vectors in the bases give you the dimensions. So again, we are asked to find the coordinates. So again, the coordinates, because this is dimension 3, so the coordinate is actually an element in R3. Okay, even though the vector space is not have anything to do with R3, but the coordinates is. All right, and findings of this transition matrix is the same. You have to find the coordinates of these vectors with respect to different bases. And I would not go through it, but just want you to know they are all the same thing. Everything's the same computationally. Okay, so the last thing we want to do, is to go back and look at why we have these relationships where where all the computations that is done in this video is based on. So the computation is all based on this relationship. And the question is, how do you know this is true? And especially, how do you know actually this is how you compute this transition matrix? And it's not difficult. Everything is just by definitions. So let's look at the proof. So again, you have two bases. Sometimes you call this a starting basis or the O basis if you are trying to compute transition matrix from B to B prime. So again, you call this the starting basis, the O basis, like this is the end basis or new basis. Some books use notation like that, so I'm just writing it down so that you know. Okay, so let's do the computation. So suppose these are the two bases we have for a vector space, which is of dimension 2. And now let's assume that the basis U1, if you try to find a coordinate with respects to this basis, and you found A and B, that's the coordinate. Let's say this is suppose this is the hypothesis. These are assumptions. Okay, so again, we assume that we have U2. Okay, that's vectors in basis B, and we don't want that U2. That's not what we want. We want the coordinates with respects to B prime, and suppose those are CD. Now, by definitions, okay, this is nothing but definition. By definitions, these are coordinates, right? Coordinate with respects to B prime, right? So these are the numbers A, B that goes into here. These are the numbers C, D that go into here because this is the basis vectors. So these are the basis vectors. These are the basis vectors. The number are the coordinates. The numbers are the coordinates. The number are the coordinates. These numbers are the coordinates. Okay, that's definitions. So if you assume that this coordinate is this, the coordinate of U2 respect to B prime is this, then this must be true. This must be true. Okay, now you take a vector V in V, okay, right? And because U1 and U2 is actually still a basis, so any vectors V, this vector V is going to be spanned by U1 and U2. So we have some K1 of this and K2 of this. So V can be written like that. V can be written like that. Now, be careful though. If V can be written like that, do you know the coordinates of V with respects to basis B? What's that? What is the coordinate of V with respects to basis B if you can write V like this? And U1 and U2 is nothing but the vectors in this basis B. So actually, if you have V equal to this, then the coordinates is going to be K1, K2. Okay, again, this is purely by definitions. All right, so if you have V, and let's say it can be written like this, and your U1 and U2 can be written like that, so just do some algebra, multiply, substitute U1 as this, substitute your U2 like this, and K1 here, K2 here, and multiply. So if you multiply and regroup, you will get that. Multiply and regroup, you get that. Simple algebra, nothing fancy. So, which means that, okay, again, okay, this is also critical. So now, this is the V, right? This is the V, right? This is the V. And if you can write V as something multiply U1 prime, something multiply U2 prime, and your U1 prime and U2 prime are bases, are vectors in this basis. So again, this is actually the coordinates of V, same V, the coordinate of V with respect to B prime, respects to B prime. Why? This is the basis in B prime, right? So which means V, okay, same vector V, if you write the coordinate with B prime, that will be this. And this is written as a matrix product like this. Let me say that again. This is written as a matrix product like this. And what is this? We know that already, right? And so you will see that VB prime is this matrix multiply VB, the coordinate VB. So that's how it goes. That's how it goes, right? And again, what is this? This AB, what is this? This AB is right here. This AB is right here. This AB is right here. See that? This AB is nothing but this. And CD that we have right here, CD, is nothing but this. So AB is his, AB, vector AB is this, vector CD is this. So we have that. So we have that. This is the AB and this is CD. So we have that. So that is how we establish this relationship. It is messy. If you don't know how to start it properly, you get yourself stuck with B prime, all that. But if you do it right, you will see, and again, this is just one example, but you will see in general, this is how this is proved, how this relationship is found. So all this here, okay, coming from right here, okay, all this thing is trying to give you a justification, a proof for the relationship between these two coordinates for the same vectors. All right, so your homework will ask you to do a lot of these kind of conversions, and it is not difficult if you know how to do them. So computationally, again, it's not difficult at all. Conceptually, if you are curious why you have that relationship, the solutions for your answers, the answers for your questions is actually right here. Everything's here. Okay, everything's here. The proof is here. So that is how this proof right here is how you get those relationships. And this is a very messy lecture in the sense of like computations. It's like a lot of transition. Every time you have a transition from something to something, this is a place where a lot of people will get confused because, you know, transition from something to something and then you don't really know where you are. This is normal, but with practice, you should be able to get this pretty easily. Again, because as I said, computationally, there's nothing much. Conceptually, it's pretty easy. Everything from definition. All right, thank you for your attention, and this is the end of this video.